All right, back from break. Let's continue on. So I hope that was useful. I hope that that presentation talking about photons and photon energies and how we can start with photon energies and determine wavelengths and frequencies and distributions of photons. So as the temperatures of objects increase or decrease, we're going to get photons radiated by those materials, and we can follow, we can predict, and then go in and make observations of what the distribution of photons really look like. So we're going to move on in the chapter, and again, I hope that was a useful introduction to all this. So now that we've got light, and it's made out of photons, let's look at a couple of effects that we can measure with these photons. Let's take a light source. Now what they've done here is they've taken a battery. Ooh, you guys remember what batteries look like, right? Here is an ammeter, and what we're going to do is we're going to get a photocell. Now this photocell, it's a glass tube, and it's a vacuum inside. So it's a vacuum tube. There's a metal plate inside here, and then there is another metal post inside the tube. Now clearly there's a gap between the two, so that when I close this, oh, where's the switch? They forgot to put the switch in. When I close the switch, current's not going to flow. The electrons are blocked. The electrons are not going to have enough energy to be able to leave the metal surface and make their way over to the post. But what we can do is we can shine a light source on this. Now the light source is going to consist of a bunch of photons. What kind of a light source should we use? If we use a red light source, the photons will not have as much energy as if we use a blue light source. Now why is that important, using blue versus red light to generate a current inside here? Well, now that we understand light's made out of photons, what we're going to need is a photon coming in, an individual, one photon coming in, needs to have enough energy to be absorbed by one electron. So one photon gets absorbed by one electron. Each electron in there is going to have some kind of a binding energy. So that electron is attached to the metal plate, and it's going to require a certain amount of energy to overcome the binding energy of the electron. Now typically inside a piece of many different metals, the binding energy is just a few eV of energy. So remember our units of eV. Well, if I can bring in a photon with 3 or 4 eV of energy, and the binding energy is only 2 or 3, that's going to be enough. So what we're going to need to make this happen, the key property here is, the key property is not how many photons. It doesn't depend on how bright that light source is. It depends on the individual photon energies. So it says that a very dim blue light will likely produce this effect, but a really bright, intense red light won't. I can shine a really bright red light onto that plate. The plate absorbs the red light, but it's not enough for individual photons to transfer enough energy to individual electrons to separate and create a current. So again, what we're looking for is a photon to come in with enough energy that the electron separates, and then some of those electrons will reach the post inside here, and that will create an electric current. We can create an electric current by shining light if the photons within the light have enough energy individually. Now, when we run these experiments, we can actually measure the kinetic energy of the electrons that are being produced. What we can do is we can determine when these electrons, the little negative particles there, come off of that plate, we are able to actually go in and measure how much kinetic energy. And what we find is, as the frequency of the light increases, the kinetic energy of the electrons goes up. Now remember, the frequency of the light, what Planck discovered and what Einstein interpreted, is that light's made of particles. The frequency of those particles is proportional to their energy by a proportionality factor of Planck's constant. And what you would expect is that as the frequency of the light's going up, that means the energy of the photons are getting higher and higher, and there's a direct proportionality between the energies of the photons and the kinetic energy of the electrons. Now, the other key feature here is if the energy of the photon drops below a certain value, then those photons can no longer cause the electrons to be released from the metal surface. So here's an example. Let's take a look at this. We're going to call these photoelectrons. What we want to do is find out how much kinetic energy. Now, speed's a little, it's funny, when you get down to the level of electrons and protons and such, we can go in and we can calculate how much velocity they have, but more importantly, we want to work in terms of how much energy they have. So we'll do the calculations of both. What it says is this. It says that something called the work function. Now, this is a piece of sodium. And for those of you who have taken chemistry or familiar with sodium, sodium's really reactive. If you can keep it away from water or keep it away from other compounds, you can make metallic sodium. Sodium is a metal, but it reacts very readily with so many materials. It's very difficult to work with. But you know, you could create a sodium metal surface and you could shine light on it, as we've shown in these examples, and you could measure what the binding energy is for an electron in sodium. And the binding energy of an electron in sodium is measured to be 2.28. This is referred to as the work function. If you remember when we defined work, work was a transfer of energy. And with a work function of 2.28 eV, that's telling us we would need 2.28 eV of energy to free the electron from the block of sodium metal. So we're going to try a couple different types of photons. One's with wavelengths of 410 and one with photons with wavelength of 550. And let's see if these are going to work. So here is the block of sodium. Here is a photon coming in. We're being optimistic. We're thinking we're going to get the electrons being... these are not new electrons. These are electrons that already existed. So the electrons are what we consider to be conserved matter particles. So the electrons were already present. Now the photons are what we consider to be transitory force particles. And so the photons actually come into existence, they get created, but then they go out of existence. They get absorbed, or in particle physics we like to call that annihilation. The photon is annihilated when it's absorbed. So let's try this out. Here are the two photon groups that we're looking at. We said group number one has a wavelength of 410. That would be a blue beam of light far into the blue end of the spectrum. And so, and the energy we're getting for those is 3.02 eV. Individual photons would have that much energy. Now, what about at 550 nanometers? Well, that's in the green part of the spectrum. Those photons would have 2.25. So we're just saying how much energy do individual photons have in the blue light, how much energy do they have in the green light. Now you can see already the blue photons are looking more likely to make this reaction happen, right? So let's go ahead and see. What was the binding energy? Oh yeah, the work function or binding energy is 2.28. Uh-oh. What does that say about the green light? Not going to happen, right? What's going to happen is the green photons come in and they get absorbed. And the electrons absorb the energy and they go into higher quantum states, but they don't leave the metal. It's not enough energy to completely separate. So the blue photons, definitely. In fact, if we look at the blue photons, the kinetic energy of this electron coming out this is an energy conservation formula. You take the energy of the photon, which was 3.02, you subtract off how much energy was used for the electron to separate from the metal, and whatever energy is left over is kinetic energy of the electron. Okay. Now in 1905, this formula would win you a Nobel Prize. Okay, when Albert Einstein received his Nobel Prize, I can't remember. It was there was more emphasis placed on the photoelectric effect interpretation, I think, than on special relativities. People were still a little nervous about special relativity. Anyway, the good old days when you could win Nobel Prizes for formulas this simple. But that's it. We're just energy, keeping track of the energy. Now, if I take that amount of kinetic energy, so energies of photons, energies of electrons, we're just balancing out all the energies, accounting for it. I can take the kinetic energy and solve for gamma. So using what we learned back in chapter 36, special relativity, what we could do is solve for the gamma factor for those electrons at 1 plus kinetic energy over mc squared. Here we go, mc squared for electrons, if you remember, 511,000 eV. It says that they have a gamma factor of, okay, it's not very impressive. So the electrons coming off 1.00001448. I really didn't need to use relativity for this. But when I went through and solved for the velocity, okay, I've got to double check that. Did that really happen, or did I copy the number over? So when I calculated this came in at 0.00170 times the speed of light, which is 511,000 meters per second. Seems like kind of a coincidence that both of those came out to be 511,000. Anyway, so what happens with the green photons? Well, I wrote nothing. I shouldn't have written nothing. The photons get absorbed. They are annihilated, so their energy goes into the metal surface, but the electrons aren't going to be leaving the surface. We're not going to see a photoelectric effect with this. Okay. All right, so that's how the photoelectric effect works. Let's see, one more example here. Photon momentum. You guys remember our 100-watt light bulb where 3 watts was in the visible part of the spectrum? Okay, here we go. So here's a bunch of photons. They don't have any mass, but they do have energy and they have momentum. Now, back in, I want to say chapter 32, which takes us a ways back, we looked at light and said that light actually exerts a force. We can write that force as the time rate of momentum, and since E is equal to PC, we could write that as 1 over C times the power. So if I know the power of a light source, I can divide that by C, and that will tell me the force. And again, we're only thinking in terms of the visible part of the spectrum. So they've ignored the infrared. Now the infrared is also going to exert a force, but for some reason they've left that out. So we'll just take the 3 watts, divide through by C. It says the force is 1 times 10 to the minus 8 newtons. That's like 10 nanonewtons of force. Okay, so it's not a very large force that these photons are generating. We would need something bigger than 3 watts to generate a significant force. What about photosynthesis? Now again, there's a lot of reading here, but it says plants basically are absorbing photons of a certain energy, and they're using those photons to build chemical bonds. They're taking in carbon dioxide, they're using the energy from those photons to take apart the carbon dioxide and reconfigure the carbon dioxide into different compounds. And so it says that the light coming in, surprisingly, photosynthesis is using photons of relatively low energy. The photosynthetic mechanisms in plants, chlorophyll absorbs near the red end of the spectrum. So we're going to take 670 nanometers as kind of a representative wavelength. Now what we want to do is take that carbon dioxide. What they're claiming here is right here. Here's the important information. It says it takes about 9 photons. And if you guys have taken molecular and cell biology and you've studied all of the photoreceptor mechanisms in plants, you realize that it's complicated. There's like a type, there's a bunch of different proteins involved, a bunch of different compounds absorbing the photons in the light. So it's a complicated mechanism, but what they're saying is that it takes about 9 photons to take a carbon dioxide and embed it in some type of carbon compound. And as you know, plants make all kinds of carbon compounds from the CO2. They take the CO2 in, some of it gets made into sugars, some of it gets made into lipids, some of it gets made into proteins, amino acids and proteins. It gets converted into nucleic acids. So CO2 is kind of the go-to compound for bringing carbon in to make all these carbon compounds. So I picked out one of my favorite organic compounds. I think I've already mentioned glucose. So the formula here would be 6 CO2s plus 6 waters would enable us to make 1 compound of glucose and release 6 O2s into the atmosphere. Now from what they're saying, that would take 54 photons. It takes 9 photons for each one of the CO2s because there are many steps. This is not one reaction. This happens in many, many steps. As you know, for those of you who have taken those classes. The energy of an individual photon being taken in by the chlorophyll works out to be just 1.85 eV. Again, the plants are using, and you feel like taking the plants saying, plants, there are these higher energy photons in the blue part of the spectrum out there you could be using, but they're going, no, we're fine, we're just going to use the red photons to take the energy in. Anyway, those photons have an energy of 1.85 eV using our newest, most favorite formula. If I take 54 of those, surprisingly enough, that works out to be just about 100 eV. So it says running that reaction once, and again, there's many, many steps involved here, but creating 1 molecule of glucose requires about 100 eV of photon energies. Okay, so I've absorbed enough photons that they add up to be about 100 eV in order to create glucose. Now, it says in the problem, when we metabolize this glucose, when we use this can be thought of as storing energy in the chemical compounds. When we reverse this reaction and bring in oxygen, and if we just take glucose and oxidize it in a lab or something, we catch the glucose on fire, that releases about 30 eV. So photosynthesis then is about 30% efficient. What we find is that of the 100 eV that came in, about 70 eV of that is lost along the way. So that's just going to end up as thermal energy in the plant. But about 30 eV of that energy is still available in the glucose when we run the reaction in the opposite direction. And as you guys also know, when you metabolize glucose, you just don't react it directly with O2. Again, there's a whole series of steps. Step by step, you take out that energy of the 30 eV. Anyway, photosynthesis appears to be about 30% efficient in terms of storing the energy, and then in metabolizing that energy, there's going to be another efficiency. Of the 30 eV available, how much of that do we actually utilize in generating our own compounds or in mechanical energy, moving around and such? Okay, let's move on to another topic here. Again, it's a photon topic. This chapter should just be called photons, right? So what happens if we go higher in energy? What if instead of photons in the visible part of the spectrum, or the ultraviolet, what if we go to really, really high energy photons, let's say in the X-ray part of the spectrum? Well, these X-ray photons have so much energy, they're not going to be absorbed. they're going to run into different things. They're going to run into the electrons, they're going to run into the nuclei, and if an X-ray runs into an electron, the electron it separates, it becomes ionized. And this is what we call ionizing radiation. So there's kind of safe radiation that feels good. You know, if you're absorbing photons in the infrared, that feels pretty nice to have your molecules vibrate a little bit. But when you go to these really high energy photons, then they begin to ionize the electrons. The electrons are separated, and that takes apart your molecules. And having your molecules taken apart is risky. If it's a DNA molecule and that molecule gets taken apart, the information at that particular DNA base could be lost. And so these are more risky, more dangerous, these high energy photons. So again, it's energy photon. It's the photon energy that determines what the photons will do. So in this case, they're saying that there's this high energy photon coming in. Now I have to say I take issue with photons being represented as little wavy things. So now on this one I left the little red wavy thing there, but I replaced it with a nice straight line. Hey, photons, electrons, they're both particles. They both have wave properties. I don't see why photons get referred to as waves and electrons get referred to as particles. They're kind of all particles that have wave properties. So anyway, I went with the blue line. So here is my photon coming in, and then it runs into the electron. Now, in the collision, the photon is going to transfer some of its energy and some of its momentum to the electron. So that's kind of like back in Physics 3A, Chapter 9, like with collisions. Yeah, we actually get to use some of the very same principles here. So energy gets conserved, total energy is conserved, momentum is conserved, and momentum is conserved in the x direction, and momentum in the y is conserved. Now, what that says then is for a certain energy photon running into an electron, at different angles, depending on what the angle, the scattered angle is, the photon could end up transferring a little bit of its energy or more of its energy to the electron. The electron will end up acquiring enough energy that it ionizes. The electron just takes off, and then the photon is going to head off in some other direction. Now the photon coming out, what this suggests then is the photon coming out will not have the same energy it had coming in. The photon has transferred some of its energy, and so the photon coming out will be at lower energy as a result. And again, this is something that we can go into the lab and we can measure this effect. This is called the Compton effect, after Arthur Holly Compton, who ran the experiments. I guess he was also involved in some of the theoretical work behind this as to what would we expect, and then went in and actually was able to set up these experiments using X-rays and establish that this really does work. So again, we're going to be treating the photons as particles. Now I think we did this in the previous chapter. The symbol for an electron is a little e with a minus sign on it, so that particle is my electron. This particle is my photon, and the symbol for a photon, for better or worse, is gamma. So that's the same symbol as the gamma factor. So we've got to be careful with that. When it's drawn like this, that represents a photon. So here comes the photon in. Here is the photon leaving at angle theta. Here is the electron, which has received a bunch of energy. It's ionizing. It's heading off on its own, and that's at some angle. Now, I'm not going to... The whole derivation is here. The textbook goes through a derivation of some formulas, and those formulas are going to enable us to determine, for a given photon energy coming in, what will be the energy of the photon coming out, what will be the energy of the electron, and that's also going to be related to the angle. So energy conservation in this reaction would say, I've got a photon and an electron, when I start the reaction, well, at the end of the reaction, I still have the photon and the electron. So the same particles are coming out as went in, but their energies are different. So if I refer to this as an AB goes to CD reaction, I can say the energy of particle A plus the energy of particle B equals the energy of particle C plus the energy of particle D, and that is energy conservation. Now, the energy of the electron sitting there basically at rest. So an electron moving around inside some material, its kinetic energy and its potential energy are fairly low compared with the X-rays. We just neglect the energy of the kinetic energy of the electron starting off. But we can't ignore its mass energy. So again, this is a nice carryover from special relativity. Hey, special relativity, it's for real. Nature really works this way. So now the M here seems like it's missing something, and that's because when we get a lot of factors of C in these formulas, what we do is we do a shortcut method. If I'm going to do a bunch of derivations, instead of writing MC squared, MC squared, MC squared all the time, I'll just write M. And then I'll do all the algebra, and at the end of the algebra, I can convert M's back into MC squareds. I can take anything that's PC, replace it with just P, and then convert it back. Now again, I'm not going to go through the details of this. If anybody who wants to stop by office hours, we can go through it. But we're writing down a formula for energy conservation. We're writing down a formula for momentum conservation in the X direction and one in the Y. And then we're just using some formulas from trigonometry, and we are using a bunch of algebra and some formulas from special relativity. Once we do all this, this is the formula we get. We get that the energy of the photon being produced, 1 over that energy, is equal to 1 over the energy of the photon we started with, plus 1 over the mass energy of an electron times 1 minus cosine theta. So you're thinking, wow, where did all that come from? And it came from here. Okay, so again, I'm not going to go all through the derivation. What I will do is I'll come back and just refer to this. So you guys know enough about energy and momentum conservation at this point that you can look at this and say, yeah, looks reasonable. So the photon comes in, it's got a bunch of momentum in this direction, and as a result, the particles coming out combined are going to have their net momentum is going to have to continue to be in the forward direction. That's what's going to happen. Now, the momentum coming in is entirely in the X direction, but because the photon can scatter at different angles, that says that these particles, well, it's like playing pool, right? If you hit a pool ball to the side, that's going to scatter at one angle, and or the ball coming in scatters at some angle, and the ball that was at rest now is headed off at some different angle. But we know that the combined momentum effects have to match, and that's what we've written down here. So again, just following the formulas, assuming that special relativity works and that quantum mechanics works, makes a set of predictions, and we can go in and check. This is the formula in terms of energy of the photons. This is the formula in terms of wavelengths. So depending on the problem, we can answer either set of questions. Now, what we can remember here is that for photons, the wavelength of a photon is given by hc over E, and that hc is 1240 eV nanometers, and that if the electrons are the targets, we're imagining these X-rays come in, they could run into nuclei, but we're specifically looking at the case where they have run into electrons. Electrons are much lower mass, and so because of the much lower mass, the energy of the photons coming out, the ones that have hit electrons will have different characteristic energies to them. All right, so those are the formulas, those are the numbers. Let's try an example. So what we're going to do is we're going to take X-rays. Now they've started by giving us wavelength information, 0.14 nanometers. they're scattered from a very thin slice of carbon. So what we're saying here is that we're going to get a really thin slice of carbon. Now, why do we want it to be thin? And that's because we want to be able to see the photons coming out the other side. So we want something that's thin enough that the X-ray photons likely will only hit one electron. Okay? A lot of X-rays will just go straight through. The X-rays will make it all the way through. They're not going to hit anything. They're going to miss everything because it's such a thin film of carbon. But occasionally we're going to have an X-ray that hits an electron in there, and those photons are going to scatter at some angle. That's the idea with this. Now here it's suggesting the photons could scatter at any angle between 0 and 180 degrees, and that turns out to be true. So when we run these experiments, this scattering angle of the photon could run between 0 all the way to 180. Now I could work in terms of wavelength or energy. They've given us information in terms of wavelength. So I'm going to go ahead and use the wavelength formula. And I'm just plugging numbers in here. So if I put in 0 degrees, I'm saying the photon did not scatter at all. It continues in the forward direction. If I solve for the wavelength coming out, I find the wavelength is unaffected. Now I'm using picometers instead of nanometers. I moved the decimal by 3 decimal places. Okay. See, they are down to 0.140 nanometers, down to a fraction of a nanometer. I went ahead and converted into picometers because it's 1,000 times smaller now. These are X-rays, 1,000 times as much energy. The wavelengths are 1,000 times shorter or more than that compared with visible light. So this would be the wavelength, and the energy that we've calculated would be the energy of those photons coming out. Now for part B, it says what would happen as the scattering. Oh, and what I should also mention here is that means that the photon missed. If the photon goes straight through and is unaffected in terms of its angle, it says those photons have not transferred any energy. They didn't run into anything. So these formulas include the possibility that the photons missed all of the electrons. Now, if the photons coming out have scattered at 90 degrees, that's saying that they ran into something. And I can put the values in. Cosine of 90 is 0. That tells me that the wavelength coming out, the photon's wavelength, is a little longer. The energies of those photons, let's see. The original photons had energies of 8.86 thousand eV. These photons coming out have 8,710. So you can see there's energy missing. Specifically, there's 150,000. Is that right? KeV? Oh, it's 151 eV. Yeah, so the electrons coming out here are coming out with a kinetic energy of 151. So whatever energy didn't come out with the photon is now going to be kinetic energy of the electron. We've ignored the binding energies in these cases because typically it's a small effect. There was more derivation stuff I had on this. I just went ahead and did part C here. When I carry out this calculation, I get 144.9. This is the energy of the photon coming out, and this time we've been able to transfer more energy to the electron. So again, Compton effect, high energy photons coming in, transferring energy. Here's some more useful formulas that you can write down. These are formulas directly in terms of energy. So if I take the formulas that we've already derived and switch them around, I can show the energy of the photon coming out depends on this, and the kinetic energy of the electron depends on this. You can try these out if you want. All right, now we've mentioned this before, but quantum mechanics says that all the fundamental particles in nature have wave properties to them. They have frequencies and wavelengths, and we can use those to determine interference effects. Now this problem is a little crazy because it's asking us to find the wavelength of a ball. This is a 200-gram ball. I don't know, is that like a baseball or something? 200 grams, it's moving at 15 meters per second. What would be its wavelength? And I'm never quite sure about these problems. Can we really use these formulas to apply them to something like a baseball? A baseball doesn't seem like a fundamental particle to me, but let's go ahead and humor them. We'll just put the numbers in. Now they call this the de Broglie wavelength, and I typically cross this out, but I forgot to this time. It's just the wavelength. It's just the wavelength. It's not the de Broglie wavelength. Anyway, here come, oh, yep, baseballs. Here we go, baseballs coming in. Ooh, this takes us back to chapters 34 and 35. I think before when I said chapter 32, I meant chapter 31. Chapter 31 is where we're looking at electromagnetic field propagation. Anyway, yeah, when we were looking at photons back in chapter 31. Here's a bunch of baseballs coming in. Here is an opening, and so we're going to say, would baseballs really create a diffraction pattern? If we throw a bunch of baseballs through a slit of a certain width, could we create a diffraction pattern? Could we have baseballs that just spread across the screen? Well, let's take a look and see. If we solve for the wavelength as hc over pc, this time I am going to, rather than use hc over pc, I'm just going to use h over p. So here is Planck's constant. Here is the momentum. Now I went back to calculating momentum. This is a baseball, so it's m times v, and the momentum is 3 Newton seconds. So if you guys like going back to these everyday kind of objects, this is a good example to be taking a look at. So it predicts that this baseball has a wavelength of 2.2, 10 to the minus 34 meters? Really? So it says we won't see the diffraction effect unless the slit is down to something of the order of 10 to the minus 34 meters. That's not going to happen. Okay, so I'm never sure about these examples, if they suggest these objects do have wave properties or they're unobservable. Anyway, I'm going to move on. It was just kind of, a chance to throw some numbers into the formulas and see what it would. Oh, here we go. Now this is one you guys want to be able to work from. Here is an electron. What would be the wavelength of an electron that's been accelerated through an electric potential of 100 volts? Now this we use in an electron microscope. So if we're using a regular light microscope, that's using photons. And so for an electron microscope, instead of using photons to do the imaging, we would use electrons. Now the nice feature of the electrons is we can have the electrons, we can generate electrons that have really, really short wavelength, and short wavelength turns into higher resolution. Visible light photons, they're at least 400 nanometers in length, and that means the resolution doesn't get much better than 400 nanometers, and there's a lot of structures that we want to see in our microscopes that are smaller than 400 nanometers. So we can use electrons for these microscopes. Now, of course, our eyes aren't going to be able to see those electrons. We're going to have to use instruments to sense how the electrons have been scattered, and those instruments will have to show us pictures of the image that the instrument has determined based on the pattern of electrons coming through. So at a kinetic energy, when they say 100 volts, that means the electrons coming out will have a kinetic energy of 100 eV. Now the wavelengths are going to be given by hc over pc. We've got the kinetic energy. How do we get from kinetic energy to momentum? Because that's what we're going to need. So a couple of, first of all, these are the general equations. Planck's constant, in terms of not joules, but in terms of eV, is 4.14 10 to the minus 15 eV seconds. And that says that the energy of these electrons coming out well, the mc squared is like 511,000. So we're going to have an additional 100 eV of energy. We can calculate the frequency. So these electrons have a frequency of 1.23 10 to the 20th per second. Did they ask about that? I guess I added that in. So I actually went through and calculated the frequency as well. So I went through and calculated the frequency of an electron. Now let's move on and see about the momentum. Now that could be given as m times v. Adding some factors of c says that we could write this as mc squared times v over c, and the velocity I'm getting from here. So the velocity of 2 comes from 2 times the kinetic energy over mc squared, square root. And that gave us something that was 0.0198 times the speed of light. So these electrons, even at 100 volts, are starting to travel at 2% of the speed of light. 5.94, 10 to the 6 meters per second. What we can do is plug that into the wavelength formulas that we have right here. So the wavelength formula, the HC, is going to be 10.4 eV divided by nanometers, and the momentum we've calculated from here is 10,120 eV. So putting those numbers in gives us a wavelength. These electrons are going to have a wavelength of 122 picometers. So these are really short wavelengths. And again, if this is part of an electron microscope, we're going to have really high resolution for this. Okay. All right, we've got, how much time do we have left? We have one last topic in the chapter, and we've got some time left. I think we'll be fine. You guys, this is probably the topic that you guys have seen most in other classes too, in chemistry classes or whatever. We're going to be looking at models of the atom. This is often drawn as a representation of hydrogen. You got a proton and an electron. The proton, or the nucleus, if we generalize this to other elements, is often represented as being about 10 to the minus 15 meters, like a femtometer across, whereas the size of the hydrogen atom is about 100 picometers. So you can see the nucleus, they have not drawn this to scale. This is 10 to the minus 15 versus 10 to the minus 10. That would say the nucleus, if I look at the diameter here, the size of the nucleus would be 1/100,000th the size. So this would be a tiny, 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 really tiny speck. It would be hard to even see the proton compared with the size of the region that the electron is filling up. And I want to get that statement out here again too. A lot of times you hear these things like atoms and molecules are mostly empty space. I think that's a misrepresentation. What we're going to find in the next few chapters is that the electron is not a point particle going around in some kind of an orbit. The electron has to be represented as a probability distribution, and that probability distribution fills the regions of the atoms and of the molecules. If you've been in a chemistry class or a biology class where you're looking at different molecules and kind of how the electrons fill in the space, you know that you have to think in terms of atoms as being more or less spheres, not something orbiting, a point particle, but something that fills space. And what fills that space is the electron probability. So this is an early model, back when electrons were first discovered. It was found that if you took, so this is an experimental setup, if you took a sample of some gas, let's say it's hydrogen or helium, and you put it into a high voltage tube, what you could do at high enough voltages, you could generate electric currents. You could ionize the electrons. The electrons would be pulled away from the nuclei, and you no longer have molecules of H2, you just have individual electrons and protons. So here are the electrons going one, if it's hydrogen, here are the electrons going one way, here are the hydrogen nuclei, the protons, going the other way. And what happens in this case is that we generate light. And we don't generate light with a complete spectrum like we see down here. We generate specific energy photons. Only photons of very definite energy or very definite wavelength will be generated if we're dealing with hydrogen. Now, if we put a different material in that tube, like helium, the pattern is different. And the question became, and this was back in the 1800s, people were doing these experiments and they're going, well, why do these specific wavelength photons get generated? What's so special about these particular lines in the spectrum? And why does each element or each compound, or why do they have their own pattern to them? And here's the complete pattern for hydrogen. So if you look at the hydrogen spectrum here, there's a series of 4 lines in the visible part of the spectrum. But if you look in the infrared, if you get instruments out to look for this in the infrared or the ultraviolet, you find out that, what is it? There's 4 lines, 1, 2, 3, 4, that are in the visible part of the spectrum, but there's a whole series of additional lines in the UV and in the infrared. Now this has these different wavelengths written in to kind of guide this. And what Niels Bohr came up with was an idea of the electrons exist in quantum states. So here are the electron quantum states. There are higher states and lower states. And when an electron in a higher energy state drops to a lower energy, that energy has to be conserved. It's got to go somewhere. And it goes into the creation of a, oh no, it's a wavy photon. I didn't get that changed. Okay, cross out the wavy photon. We just want a straight line. So the photon is going to carry energy away from that. A photon has been generated. Similarly, we could turn this picture around. We could have a photon bringing energy in, being absorbed by an electron in a lower state and a higher state, and that photon needs to have just the right amount of energy to boost the electron from one quantum state to another, and that was the explanation for these spectral lines. So these energies, these particular energies, represent differences of energy between 2 electron quantum states in that particular element. Now, based on this model, Bohr made some incorrect assumptions. Bohr said, what would happen if the electron were actually in some kind of a circular orbit? Do not get attached to that, that's wrong. I'm hoping you guys in your physical science classes are already familiar somewhat with how we understand the probability structure of electrons. But if not, we'll definitely take a look at it in this class. But this is really outdated. If you're thinking of electrons orbiting nuclei, we need to get rid of that picture. Anyway, Bohr was able to use formulas from, well, from physics 3b, really, formulas for electric forces. Here's a derivation of what Bohr went through. And again, the assumption that Bohr made was that there were a series of circular orbits, and that each one was characterized by a certain amount of angular momentum. It turns out that Planck's constant, h, has units of angular momentum. It turns out that Planck's constant, in addition to showing how frequencies and wavelengths and energies and momentum are related, Planck's constant also plays the role of the fundamental unit of angular momentum. Now, for these atomic systems, that angular momentum would have to do with the electron in its attachment to the proton. And so Bohr represented this as a circular orbit and said that the only possible values for angular momentum were multiples of Planck's constant, but not quite Planck's constant. What Bohr argued was that there is an angular version of Planck's constant and that would be h divided by 2 pi. And that is written as h bar. So you guys get to cross your h's. When we're working in many of the formulas that we'll see in the next, well, kind of throughout the rest of the course, but certainly in the next 2 or 3 chapters, we're going to be using h bar as well as h. We'll be switching back and forth depending on which is convenient. H bar itself is viewed as the fundamental unit of angular momentum among particles. Okay, so Bohr assumed that each of these orbits had a certain amount of angular momentum. It turns out that in quantum mechanics now, full-blown quantum mechanics does predict that angular momentum is quantized, but it's not this simple. So this is not the correct version. Anyway, Bohr, using some incorrect assumptions, was able to predict what the size of a hydrogen atom would be, and the number that he came up with appeared to match pretty well what researchers had observed for hydrogen in different compounds. Now, hydrogen doesn't have a certain fixed, exact diameter to it, so that was a little bit vague. But Bohr also, by assuming these circular orbits and running a bunch of formulas, derived a formula for the energy of each of these orbits, and this is just exact. Well, it's not perfectly exact, but it's like really, really, really exact. It doesn't take into account electrons have spin and they have charge, so they have what we consider to be magnetic dipoles. There are these small effects that the Bohr model does not include, but this formula of minus 13.6 eV divided by n squared works really, really well. So this is kind of what Bohr came up with. Now, he made a set of incorrect assumptions. In chapters 38 and 39, we're going to come back and we're going to do quantum physics the right way for atoms, and we'll come up with what we currently view as the correct way of thinking about electrons and nuclei and what their properties are. But in any case, Bohr was able to come up with some formulas that gave the correct size of atoms, hydrogen in particular. Bohr was able to predict that there was an existence of different quantum states with different energies. Now, he didn't get the pattern of quantum states entirely correct. On the other hand, the energy formulas he came up with work for hydrogen. And so the very lowest energy state for the electrons in hydrogen has a binding energy of minus 13.6 eV, predicted from Bohr's model, and that turns out to be correct. When we come back and we do the complete, full-blown quantum mechanical calculation, we find out we get the same formula that Bohr did. But we feel it's for the right reasons. That Bohr made some incorrect assumptions, but ended up with some offsetting effects that left him with the correct formula. We're going to claim that our complete quantum mechanical view of the atoms that we see in chapters 38 and 39 are the correct way of getting these numbers. So that's the lowest energy state. Now, if you follow that formula that we wrote down, and here it is one more time, it's this formula right here that we're coming back to. The 13, that's a decimal. 13.6, there's a point there, eV divided by n squared, where n is the energy of that particular level. So n equals 1 are the electron distributions that are closest to the nucleus. N equals 2 is another set of distributions farther out. N equals 3 is and so forth. And so we can put in those values of n, and here we go. So if this is the energy, now this is the energy in terms of the mass of the electron, the electromagnetic force constant, the charge of the electron, and Planck's constant divided by 2 pi. That's the formula for the energies of these different states. Numerically, that gives us negative 13.6. It's a minus sign because the energies are dominated by a potential energy. So the energies here are both potential and kinetic, but the potential energy is deeper than the kinetic energy, and that holds the electron to the nucleus. So if I put in different values of n into this formula, these are the energies we get of the different quantum states within hydrogen. Okay, here's a diagram, an energy diagram. Now, when photons are created or annihilated, those photons will have energies that are equal to the difference between where the energy of the electron started and where it ended up. So, for example, well, I'm just going to write the formulas this way for now, I guess. The energy of the photon then would be minus 13.6 eV times 1 over n squared for the initial state minus 1 over n squared for the final state. This is referred to, the stuff out front here, the 13.6 divided by hc, is referred to as the Rydberg constant. Not considered to be that important anymore since we have a more fundamental understanding of how this is all working. Now, this is an example. It says, use this energy diagram to determine the wavelength of what are called the Lyman series, or the Lyman transitions. So the transitions we're looking for here, these are the energies of the different quantum levels. So the lowest would be 13.6. The next lowest would be at minus 3.4. So if I have an electron in an excited state of n equals 2, and it transitions to state 1, that's a difference of 10.2 eV. And that's the energy of the photon that would be created for that transition. So I think I'm going to end up going over a bit here. I apologize for that, but I do want to make sure that we get a look at some of these examples. So again, this is the formula that has been derived. It was derived using incorrect assumptions. We'll come back in chapter 39 and show how it actually would be derived quantum mechanically, full-blown quantum mechanically. This is the energy value that we obtain from this formula, where little k is the electromagnetic force constant that we used back in chapters 21 through, let's say, chapter 31. So from chapter 21 through chapter 31, we were looking at electric and magnetic forces. And the force constant for all of those examples, we use little k. Now, the textbook kind of went back and forth between using little k and 1 over 4 pi epsilon naught. I'm going to stick with little k here. But this is the electric magnetic force constant. The energy of the photon generated in going from excited state 2 to ground state 1 in hydrogen is 10.2 eV. Using our wavelength formula, hc over the energy, we can plug those numbers in, and it says the wavelength would be 121. So the energies of these photons, their wavelengths, show that they are in the ultraviolet part of the spectrum. Let's look at one more example here. Let's look at a transition from state number 6, energy level 6, to energy level 2. Again, this is a formula that at least originally was derived by Bohr. And here's an electron in energy level 6. Now notice the reference we're working from here. This is 0 energy. And when we're working in terms of potential energies and such, 0 energy becomes the point at which the two particles are attached. So 0 energy would mean that the particles are just barely attached to each other. They're right at the threshold of separating and going their own way. As we drop below 0, the energies become more and more negative, and that means that there's a binding energy. That the electrons now, with this negative overall binding energy, which includes both kinetic and potential effects, is not going to be separating unless energy comes in from somewhere, unless a high energy photon comes in. These electrons are going to stay attached to the nucleus. Now in hydrogen, going from state 6 to state 2, if it's hydrogen, we can continue to use this formula. Hydrogen is characterized by just one proton and only one electron. And so the electron is really just, the formula is based just on the interaction between the electron and the nucleus, just two charges. We're not going to complicate it with more electrons, and the formulas remain fairly simple. So here is the energy of level 6 based on this formula. Here is the energy of level 2. I can take the difference between the two. Now this is subtracting negative values, which, draw a diagram. So if I take this negative value and I subtract this negative value, I'm going to get something positive because this value is bigger. Even though both numbers are negative, I'm subtracting a smaller, a lower negative value. And so the energy we get in this case from taking the higher energy quantum state, subtracting off the lower one, gives us a photon energy of 3.02, and it has a wavelength of 410. Now that is in the visible part of the spectrum. That's kind of in the blue region, 3.0 EV or 410 nanometers. We're using those same formulas of wavelength is equal to hc over energy. Okay. And I think I'm going to leave it there. I think we're well, let's take a look at this last one. It says we're going to absorb a photon. We're going to annihilate a photon. Determine the maximum wavelength that hydrogen in its ground state could absorb. So by maximum wavelength, it's kind of hard to think in terms of wavelength. What you want to do, I think, is immediately think in terms of energy. So if they're asking for the maximum wavelength of a photon, what they're asking for is the minimum energy. What is the minimum energy a photon could have that would enable it to take an electron in the ground state and raise it to an excited state? Well, the lowest energy photon would need to be able to go from state 1 to state 2. And that photon would have energies of 10.2 eV. So again, using those same formulas. Now I wrote this out to more significant figures than I probably should have. This is often written as 13.6, and that's fine. Don't worry about all these extra digits. But I wrote it out, 13.6057 EV, got a few more significant figures. These are integers, basically, so these are very, very precise. So the energies we're coming up with here, but energies between these states, 10.20 EV. Here we go. So a couple of transitions. To get from state 1, the ground state, the lowest energy state, to the first excited state would require photons of this energy. Those are the ones that are going to get absorbed. If we send in a whole range of photons with a whole range of energies, the ones in and around 10.2 eV will be absorbed, and those electrons will jump into a higher energy state. Now to get to state 3 from the ground state would require energy 3 minus energy 1, and that works out to be 12.1 eV. So those photons would also get absorbed. So one by one, we can look at the different possible transitions. How much energy would it take from state 1 to state 4? And we can see what which photons will be absorbed. There's one more example with helium. I will let you guys take, okay. How do we change this for helium? Now it's not helium, it's helium plus. This is helium that's already lost one of its electrons. So helium is element number 2, and so helium has 2 electrons if it's neutral, but if 1 electron has already been removed, there's only 1 electron left. And if there's only 1 electron left, then the formula, the Bohr formula, will work if there's only 1 electron. Now, the Bohr formula has to be modified. What we find is, if there's only 1 electron, but the nucleus now has more protons, we have to take into account the number of protons. Helium has 2 protons in the nucleus, and when we go back and rederive the formulas, we end up with a factor of z squared. So, so that gets added into the formula. So it's the same formula as before. We have the 13.6, negative 13.6 EV, but now we got to multiply by a factor of 4. So what that says is that helium plus will have the same pattern of different energy quantum states, different energy levels, but those levels will be 4 times deeper. There will be 4 times as much binding energy for each one of those. The ground state, instead of 13.6 EV, will be at negative 54.4. So a transition, which transition are they talking about? Oh, they're asking about ionization energy. Okay, so what they're saying is, now what they want to do is they want to take an electron, in the remaining electron, there's only 1 more electron left, they want to take it all the way past all of the possible quantum states, all the way to ionization. Now, ionization is at, by definition, 0 energy. That's the energy that everything has been calculated in reference to. The ionization level is the reference. And so we can take the 54.4 EV, that's it. So a photon coming in to remove that remaining electron in helium plus would need to have an energy of 54.4. That's a pretty high energy photon. That's quite a ways into the UV. And the wavelength of that would be at 22.8 nanometers. Okay, so I hope that was useful. We did go over, I apologize for going over. I hope it was useful, the additional time that we've made use of here, because, yeah, and now we're into the summary. Okay, so stop by with whatever questions you guys have. And again, thank you for your patience. Hope to see you guys in office hours, and we'll take a look at all these examples.